Hello, everyone. Let's start with our third lecture. We're finally getting into the more technical part of this topic. In this lecture, we're going to talk about the basic methods for um, image processing that are also used in many computer vision applications. And we're basically going to cover chapter 3 of our book. This lecture is divided into 4 parts. Part 1, we're going to talk about intensity transformations. These are the most basic image processing transformations. They're usually based on applying some sort of arithmetic functions to the pixel or to the neighborhood of the pixel. But then histogram processing, as the name says, we're going to be understanding and using the statistics of the image, the distribution of pixels intensities throughout the image. Then the core part of the course are these things that we're going to be talking over and over again. We're going to learn in the context of linear spatial filtering, the concept of correlation, and most importantly, convolution. Please pay attention to that. Convolution comes back and back again in many computer vision and image processing applications. And finally, the other essential methods that we're going to be studying in this chapter is image sharpening using the concepts of derivatives, image derivatives. These are convolution and derivatives are the two most important concepts in this whole topic. They are most important because they come back over and over again. They are applying in various topics, in various methods. So please pay good attention to these two concepts and histograms as well. There are for a great deal of methods that use histogram processing. Let's start with intensity transformations. We've learned from the previous lecture that spatial domain processes are based on the application of some sort of operator over the original image. And this operator is going to apply a transformation in the original image to generate an output image. That's this G here. And this operator T may be defined on single pixels, where we're going to apply to each pixel in an image. Let's be reminded that each pixel in an image is nothing more and nothing less than an element of a matrix. So we're basically applying a processing to each element in a matrix. That's what's an intensity level of single pixels. That's what it means by applying transformation on single pixels. Or we're going to apply a transformation using the neighborhood or a point. In this case, this transformation is going to be called neighborhood processing. An operator defined on the neighborhood, what you do is that this operator is going to be applied on a moving neighborhood of the image. So moving the center of the neighborhood from pixel to pixel. Let's first understand the concept of neighborhood. So you have a pixel here, and we can use, we've learned about neighborhoods on the last lecture, that we can have an 8th neighborhood, a 4th neighborhood, we can have a 16th neighborhood, which is just the pixels around a particular pixel. So what an operator defined on a neighborhood is, it's going to use the values of the pixels in the neighborhood and apply an operation changing the value of the pixel in the middle. And this is going to be applied on a moving center. So it's going to be applied from the top corner to this pixel, and then we are going to move it and apply to the next pixel. Then we are going to move it what? Move it this submatrix or the neighborhood that's also called the window around which the application, around which the operator is applied. So these are also methods that are called moving window methods. We are moving a window around the pixel, doing some sort of arithmetics around the pixels. That could be, the arithmetics could be just calculating the average or some other functions, using the values of the pixels around, and then we're going to changing the operation is going to change the value of the mid pixel. Again, the operator T uses the values of the pixels in the neighborhood to yield an output value at its center, at the center of the neighborhood. Let's start with some pointwise methods, which are contrast stretching and thresholding. Contrast stretching it produces an image with higher contrast, meaning that it's going to darken the intensity levels below a certain threshold K, and it's going to brighten the levels above K. So these are two examples of contrast changing. Now, actually, A is an operation of contrast stretching, and B is an operation of binarization. We're gonna learn about binarization in a second. Let's understand contrast stretching. So you see, these are on the x coordinate are the pixels intensities of the original image. Now we are going to each intensity value of the original image is going to be mapped using this function here, this function here, to a value of intensity on the output image. So for instance, let's pick up this pixel that's below K, which let's guess a value. Let's say this pixel has value 10, just for the sake of an example. Given this transformation, that's this function here, this pixel is going to be mapped to a value, let's say 2, because it's on a lower part of the scale here, any y coordinate, that's the output image, representing the output image intensity, and it's a much higher value on the original image. So it's darkening the intensity levels below K. And let's see what happens with an intensity level above K. Let's say this could be an intensity value 15. And this function here is going to map this value to a much higher value here. Let's say 15, but just for the sake of an example, we'll be mapping to 50. So this will be moderately dark. It's going to be quite bright on the output image, whereas this would be a kind of not that dark and not that bright, but will be below the threshold K. This is going to be mapped to a much darker pixel value. This is the operation of contrast stretching. This is applied on each pixel of the image. So that's a single pixel operation. Whereas binarization, what binarization does, each pixel value on the original image that's below a certain threshold, say K, are going to be mapped to 0. So they are going to be black, pitch black. Whereas pixels above, with intensity values above K, are going to be mapped to white, to very bright pixels, right? What we get in the end, let's get a This is an example of an image where I'm applying a rather it's a more complex operation that we're going to see in a minute, but we're basically applying this idea of thresholding here, where the pixels that are bright are a little bit whiter become quite bright, and a little bit darker are going to become totally black. Okay, let's move on. There is quite a number of examples that we have to run through in this lecture before we move on to the next part of the lecture. These are some simple but very powerful methods that can be formulated with intensity transformation functions. The chapter that we are reading now, chapter 3, uses intensity transformations for image enhancement, meaning to make the image better, to make the information in the image more apparent. So that's the meaning of enhancement here, is the process of manipulating an image to achieve a more suitable result. There is no general theory for image enhancement. It's basically used for visual interpretation, whereas the user is the ultimate judge. The user is going to be telling if and how well a method works or not. And for image perception, it makes the results easier to quantify. Whereas later on chapter 10, we're gonna see how these methods can be used for image segmentation, where we are gonna find distinct regions of an image, and segment them from the rest of the image, extract them from the rest of the image. Other basic point processing are basic intensity transformations. We can apply the negative. The negative, we get the value for the intensity of the original image and subtract from the highest most value in the intensity range. We can apply a logarithmic function to the intensity of the original image. Mapping, what the log is going to do is going to map a narrow range of low intensity to a wider range of output values. So for instance, the log is what we discussed here. So this is a kind of, it's not a log, right? But it's similar to this kind of transformation, where we get a narrow range here of intensity values in the original image. And these are mapped to, sorry about my bad drawing here. These are mapped to a wider range. Right? If you pick up here, you see this is a wider range of intensity values from a very narrow range in the original image. Similarly to the log operator, we have the power law or gamma operator, where we get the values, the intensity values of the original image, and put them to the power of a determined value. Let me get rid of this. Right. So you see that if gamma is 1, we have the intensity, the identity transformation. The same values here are going to be mapped to the same values there, given a particular constant. It's not going to be exactly the same values, but you get the idea, right? If gamma is greater than 1, you are going to have an exponential function. Depending on the gamma, you have a more pronounced exponential function here. And if gamma is fractional, you are going to have a similar effect as we're going to get with the log. These are the log powers, right? Well, we're going to have logs with distinct bases, right? It's basically all logs on this part of the code. This is the effect with the negative image, considering that this is the original image. That's a mammogram. Once we apply the negative, every pixel here that's dark is going to be bright, and every pixel bright here is going to be dark. You see that the same information in the original image is obtained in the output image. So why should we do a negative? Because it's easier for the human eye to spot a cancer, a potential cancer, to spot bright, dark regions around brighter contours, brighter contents, rather than spotting bright regions around darker contours. Why is that? Well, we discussed the illusions in a couple of lectures ago, and that's part of the human visual system. That's one of the characteristics of the human visual system. This is more on the power law, just putting the numbers on the gamma. You see if it's fractional, you are on this portion of the space. If it's fractional between 0 and 1, I should have said, and any value above 1, it will going to be in this part of the space. The transformation will be an exponential, whereas here the transformation will be log-like functions. Applications of the gamma corrections. We've all seen this kind of defect, right? This kind of defect when the image is slightly darker on one side and brighter on the other side. And this is the response of many imaging devices, such as various displays or printing devices. They all obey a power law. We can correct that by applying a gamma transformation from taking the every pixel on the original image to the pixels in this gamma corrected image. You see that the region that's darker is now just a tiny bit of the image. Then once you see it through a capturing or displaying device, you're going to see that when you apply this to an imaging device, these darker portions are going to become much more pronounced, whereas once you gamma correct the original image, you're going to have a better output on your on the same monitor, using the same monitor as used here. It's one of the applications of gamma corrections. Another one is you see this is a I think it's an MRI of a fractured human spine. You really can't see the fracture. The information is here, right? But the human eye, at least I can't see anything. It's too dark for my eyes. Now, if I apply a gamma correction of 0.6, we see this result here. It's slightly better to see, even though we have a saturated portion here, but we are not interested in this portion of the spine. We're interested in analyzing this where the fracture is. If we apply a gamma correction of 0.4, this is much better to see. If we go one step further, 0.3, now although it's brighter, I started losing some of the details. Look closely here on this portion of this image in compared to that. In this one, I can see a lot more details than in this one that started to get a lot of noise due to the values of pixels related to as output by the gamma correction. Have a look. Oh, I don't know. Maybe you prefer this one. Maybe you prefer this one. That's why there is no theory behind it. It depends on who the user is. It depends on how you're going to use this information on your computer vision system. More on gamma corrections. So you see, this is an aerial image of a landing of an airport, right? An airport. You see that's mostly quite bright. Now, if I apply a gamma correction of 3, we end up with this image that's a lot better, right? So I can see, check for instance this region in the image and compare to that region in the image. My eye can't see much here, whereas here it's a lot better. And if I put a gamma correction of 4, I see a lot more details in this region. And with 5, I see quite clearly. It even looks like a distinct image, but that's exactly the same image as this one, but just being corrected to better use, to better interpretation from a human eye. Piecewise linear transformation. So far, we've seen transformations. The same law applied to every pixel in the image, indistinguishably. It's the same law applied to every single pixel. But I can apply distinct laws to distinct portions of the pixel. So for instance, I can have a little threshold here where I apply one transformation, and then in another portion of the image, I apply another transformation. In another portion of, I should have said, of intensities of the image, I apply another transformation. So you can see this is the original image. That's a low contrast electron microscope image of pollen, magnified 700 times. This is the result of contrast stretching using a piecewise information like this, using this kind of function. And this is the result of binarizing the image. And finally, well, there are many other methods. These are just the basic methods at the intensity transformation, pointwise intensity transformations. Another one, the last one that we're going to see in today's lecture, is the intensity slicing, where I can, for instance, highlight a small range of pixels, a small range of intensities. I'm going to make them very bright, whereas all the rest I'm going to put closer to 0. Or if I want to make a better contrast, I can even put them to 0. And this is the result of applying, this image is the result of applying this transformation to this original image, where you can see clearly, if I wanted to highlight this portion here, I think is the aortic angiogram, right? This is the aorta, this is the heart, I think. Sorry, I'm not a biologist. So, right, if I want to highlight that, you see that there is a range of values. If you pick the values of pixels, that's very different from the range of values of all over the image. So what I do is that I know which range is this. I highlight them, I make them stronger, and I place the other pixels closer to 0. These are the pixels that I'm not interested in, and these are the portion where that's been highlighted using this function. Okay, and similarly, I can highlight as a portion of the image without changing the rest of the image, without changing too much. That this is the result of applying this function here to the original image, you can see that all the information that had been here before, they are somewhat represented here in the same way, whereas the part that I wanted to highlight is better views. It has a brighter intensity of pixels. All right, so thank you. In the next lecture, we're going to see histogram processing methods.